Salam Jama'ah, again our chapter is about, it's the second chapter this year is logarithm function. As we started by one definition, what is a logarithm function? The Napierian, we said before, the Napierian logarithm function denoted by f of x equal ln x defined over 0 plus infinity is the only antiderivative of 1 over x that vanishes at x equal 1. Again, we said that the Napierian logarithm function is denoted by f of x. Consequences, what we should know about logarithm. At first, the Napierian logarithm function denoted by f of x equal ln x. So Napierian logarithm function is ln x. Defined over 0 plus infinity. The domain of definition is 0 plus infinity. It means the x which is inside the logarithm function should be always positive. Is the only antiderivative of 1 over x. Antiderivative of 1 over x is ln x. So, a very important rule. Derivative of ln x is 1 over x. That vanishes at x equal 1, يعني ln of 1 equal to 0. Part 3. And we did solve an application about how to find the domain of certain function with logarithm. Part 3. Limits. We know that f of x equal ln x is defined over 0 plus infinity open bounds. So we can find the limit at 0 and we can find limit at plus infinity. Limit. The first rule, limit as x tends 0, and of course it's a 0 plus here, of ln x equal minus infinity. This is the first rule. And you can know it as ln of 0 equal minus infinity in your head. Limit as x tends plus infinity of ln x. Ln of plus infinity is always plus infinity. We still have two other rules that we can use directly instead of having if in indeterminated forms. First rule, limit as x tends plus infinity of ln x over x is equal, usually it's infinity over infinity, but because x is always faster and greater than ln x, we can consider it as number over infinity 0, and we are going to prove it. We are going to prove this rule. Limit as x tends to 0 of x ln x, it's also 0 times minus infinity if. You can take the value of x because it's greater and it's faster than ln x, so it's 0. And we can also prove these two limits. Proof. Limit as x tends plus infinity of ln x over x equal infinity over infinity if. So we can applicate the operator rule. It's limit as x tends plus infinity. Derivative of the numerator is 1 over x. Derivative of the denominator 1. As you know, operator rule, you can find the derivative of the numerator over derivative of the denominator. 1 over plus infinity 0. 0 over 1, 0. So the answer is 0. Also, limit as x tends to 0 x ln x. It's 0 times minus infinity if. And we said before, when we have 0 times infinity if, we should expand. But we can't expand here because it's already expanded. So what we can do, and also we cannot apply, in this case, till now, we cannot apply operator rule because we don't have a fraction. It's not a 0 over 0 or infinity over infinity. But we can make it as a fraction. How? Limit as x tends to 0. We can write ln x, and x we can write it over 1 over x. X ln x can be written in the form ln x over 1 over x. As you know, a is always 1 over 1 over a. So now we can apply the operator rule because the answer now is minus infinity over plus infinity. So by applying the operator rule, derivative of the numerator is 1 over x, and derivative of the denominator, of course, I'm sure that you did miss it or you forget it, derivative of 1 over x is minus 1 over x squared. Limit as x tends to 0, we can multiply 1 by x squared is x squared, and x by minus 1 over minus x. By simplification, x squared with minus x is x over minus 1, 0 over minus 1 is 0. That's how we can show that limit at x tends to 0 of x ln x equal to 0. Application. Calculate the following limits. Part 1. Limit as x tends to 0 x plus 1 plus ln x. Part 2. Limit as x tends to 0, not 0, plus infinity x plus 1 plus ln x. Part 3. Limit as x tends to plus infinity x plus 1 plus ln x over x. Part 4. Limit as x tends to 0 x plus 1 plus ln x over x. Part 5. Limit as x tends to plus infinity x plus 1 plus x ln x. Part 6. Limit as x tends to 0 x plus 1 plus x ln x. Part 7. Limit as x tends to plus infinity 1 plus ln x or x plus 1 plus ln x all over x. Part 8. Limit as x tends to 0 x into x minus 1 plus ln x. We have to calculate all these limits, so we can start by part 1. Limit as x tends to 0 of x plus 1 plus ln x. We have to replace x by 0. It's 0 plus 1 plus ln of 0 is minus infinity, and the answer is minus infinity. Part 2. Limit as x tends to plus infinity of x plus 1 plus ln x. We have to replace x by plus infinity plus 1 plus infinity plus ln x plus infinity. Part 3. Limit as x tends to plus infinity of x plus 1 plus ln x over x. As you know, limit as x tends plus infinity of ln x over x is 0. So it's plus infinity plus 1 plus 0 is plus infinity. And you have directly to use that ln x over x as x tends to plus infinity is 0. Or you will have an if. يعني إذا ما عملت substitute by 0 you will obtain plus infinity over plus infinity if. It's better to replace it by 0 directly when x tends to plus infinity. Part 4. Limit as x tends to 0 x plus 1 plus ln x over x. You have to know that ln x over x tends to 0 when x tends to plus infinity. But when x tends to 0, it doesn't tend to 0. Let's see. 0 plus infinity plus ln of 0 minus infinity over 0 plus. Minus infinity over 0 plus is a minus infinity plus this negligible number is minus infinity. Part 5. Limit as x tends plus infinity of x plus 1 plus x ln x. You can replace x by plus infinity plus 1 plus infinity times plus infinity, and the answer is plus infinity. Part 6. Limit as x tends to 0 x plus 1 plus x ln x. You have to replace x by 0 plus 1 x ln x. If you replace it directly you will obtain 0 times minus infinity if. But as you know from the explanation of that chapter, as x tends to 0, x ln x tends also to 0. It's a rule that you can use directly, okay? So the answer is 1. Part 7. Limit as x tends to 0 of x plus 1 plus ln x over x. If you did replace x by, plus infinity, part 7. If you did replace x by plus infinity, you will obtain plus infinity plus 1 plus infinity is a plus infinity over plus infinity is an if in determinated form. So what we can do, let me بس خليني محي شوي erase these things. Part 7, we are solving part 7. Limit as x tends to plus infinity, x plus 1 plus ln x over x. We tried to substitute x by infinity and we obtained infinity over infinity if. So what we can do? We have two different methods. First method, we can use Hopital rule. Equal, by using Hopital rule, limit as x tends plus infinity, derivative of x1, derivative of 1, 0, derivative ln x is 1 over x over 1. So it's 1 plus 1 over infinity, 0 over 1, and the answer is 1. Or you can use another way. How? Limit as x tends plus infinity. You can distribute every term of the numerator over the denominator. So x over x is 1. 1 over x is 1 over x, and ln x over x is ln x over x. As you know, ln x over x as x tends plus infinity is 0. 1 over infinity is 0, so we'll still have 1. You can use one of the two different methods. Now I will solve part 8. Part 8. Limit as x tends to 0, x into x minus 1 plus ln x. If you did replace x by 0, you will obtain 0 into 0 minus 1 minus infinity equals 0 into minus infinity is an if. 0 times infinity is an indeterminated form. So what we have to do, usually we said in class, when you have 0 times infinity if, as you know, if in 4 forms. 0 over 0, infinity over infinity, you do use Hopital rule. 0 times infinity, you do expand, and plus infinity minus infinity, you do factorize. Or in the case of radical, you have to multiply by the conjugate in some special cases. Here you have obtained 0 times infinity if, so you have to expand. So it's x squared minus x plus x ln x. And by replacing x by 0, you'll obtain 0 minus 0. As you know, x ln x as x tends to 0 is 0 plus 0, so the answer is 0. Okay, this is an application about limits. Now let's go to derivative. Again, 1 definition, 2 consequences, 3 limit, 4 derivative. As you saw in the consequences of the definition, that derivative of ln x is 1 over x always. But if we have ln u, if what's inside logarithm is more than x, like 2x plus 7, or x plus 3, or x squared plus 5, how to find its derivative? The rule is derivative of ln u is u prime over u. Example 1, if you have f of x equal x plus 1 plus ln x, f prime of x will be, or let's suppose 2x plus 1 is 2, derivative of 1 is 0, derivative of ln x is 1 over x. And if you like to take x as a common denominator, it's you can do it, or you can keep it as 2 plus 1 over x. Part 2, if we have f of x equal ln of 2x plus 7, it's not ln x, it's ln something, a factor called u. So it's in the form of ln u, and u in this case is 2x plus 7, so u prime is 2. So f prime of x equal u prime over u, which is 2 over 2x plus 7, u prime over u. Okay, like for example part 3, if you have f of x equal ln of x squared plus 1, it's also in the form ln u, and in this case u equal x squared plus 1, so its derivative u prime is 2x. So f prime of x equal u prime over u, which is going to be 2x over x squared plus 1. These are the rules of derivative and exercises about and examples about them. Now we are going to solve an application about derivative application. calculate the derivative of each function. Part 1, f of x equal x squared plus 2 plus ln x. Part 2, f of x equal ln x over x. Part 3, f of x equal x ln x. I think it's enough. Yeah. So I will keep the rules. Solutions of the application. Part 1. F of x equal x squared plus 2x plus 2 ln x plus ln x. F prime of x, derivative of x squared is 2x, derivative of 2 of 0, and derivative of ln x is 1 over x. And now part 2. F of x equal ln x over x. As you can see, we have a fraction, so we are going to use u over v. And as you know, derivative of u over v is u prime v minus v prime u over v squared. U is ln x, so u prime is 1 over x. V is x, so v prime is 1. So f prime of x equal u prime 1 over x into x minus v prime u 1 into ln x. It's simply u prime v, v prime u over v squared over x squared. Now x with x can be simplified. The remainder is 1, the remainder is 1, and 1 times ln x is ln x over x squared. That's how we found f prime of x. Part 3. F of x equal x into ln x. We have a product between two factors, so it's in the form u dot v. And as you know, derivative of u dot v is u prime v plus v prime u. So u is ln x and u prime is 1. V is ln x and v prime is 1 over x. U prime v, v prime u. So it's 1 into ln x plus 1 over x into x. The answer will be ln x plus 1. So this is the derivative of the third function, ln x plus 1. Now we are going to have an application about everything we learned today. Let f of x be equal ln x defined over 0 plus infinity. What you need to find, part 1, calculate limit as x tends to 0 of ln f of x, reduce an asymptote. Part 2, calculate limit as x tends to plus infinity of f of x and limit as x tends to plus infinity of f of x over x. Interpret this result. Part 3, find f prime of x and set up the table of variations of f. Part 4, calculate f of 1, then draw C. This is a homework for you to do for tomorrow, and we will solve it in class tomorrow, and we will deduce from this application the sign of the logarithm function and many other things like the solution of the equation ln x equal 1. I will see you tomorrow in class, inshallah. Bye.